Hi, I'm Rudy Sandbergen. In the previous video, we discussed solar radiation. In this video, we will discuss the technologies that can be used to harvest the solar radiation and convert it to usable heat. After this lecture, you should be able to explain the basic working principles of photovoltaic modules and solar thermal collectors. Name 3 different types of solar thermal collector and describe how the collector design affects its thermal efficiency curve. Let's start with photovoltaic modules. These PV modules convert light directly into electricity using the photovoltaic effect. Today's PV modules have a typical STC efficiency between 20 and 25%. Let's calculate with 22.5. Under standard test conditions, or STC for short, the module is illuminated with standard AM1.5 spectrum at an irradiance of 1000 watt per square meter. In that case, the PV module will have an electrical power output of 225 watt per square meter. We call this the peak power in watt peak, indicated with subscript P. Real-world conditions are usually less ideal than standard test conditions. In addition, we must account for system losses, such as the conversion from direct to alternating current. Therefore, to estimate the real-world system efficiency, we multiply the STC efficiency by the performance ratio, which is typically around 0.8. This gives us a typical real-world efficiency of about 18%. We saw in the previous video that the annual irradiation on Earth ranges from 1000 kWh per square meter for temperate climates up to 2500 kWh per square meter for subtropical areas. If we then assume a system efficiency of 18%, we find that the PV system can generate between 180 and 450 kWh per square meter per year. The generated electricity can be used for any application, but in the context of this course, an important application can be powering a heat pump to generate heat, which will be covered in a later video. There is also a more direct way of using solar energy for heating, using a solar thermal collector. So let's discuss that option in more detail. Solar thermal collectors that convert sunlight directly into heat come in different shapes and sizes. 2 common designs are the flat plate collector and the evacuated tube collector, shown here. Solar thermal collectors have a dark colored absorber that absorbs the incoming sunlight and converts it to heat. This heat is then extracted by a heat transfer medium, which usually is water flowing through a copper tube. This means cold water goes in on one side and hot water comes out on the other side. Usually there is also thermal insulation to minimize the heat loss to the ambient. The flat plate collector has a thermal insulation material at the rear and a glass cover at the front. The evacuated tube collector has its absorber in a vacuum tube, which very efficiently minimizes the convective heat loss to the ambient. The thermal efficiency of such a solar thermal collector is defined as the ratio between the useful thermal power output and the incoming solar power input. The power input is simply the solar irradiance G times the area of the module A. The thermal power output is the mass flow rate m dot times the specific heat of the heat transfer medium C times the delta T, the difference between the inlet and outlet temperature. By measuring these parameters, we can determine the thermal efficiency of the solar thermal collector experimentally. The efficiency of solar thermal collectors is usually measured as a function of water inlet temperature. The measured efficiencies are then reported in the datasheet that comes with the collector. In these datasheets, the efficiency is usually shown as a function of reduced temperature. Here, the reduced temperature is defined as the water inlet temperature minus the ambient temperature divided by the solar irradiance. This graph shows that the maximum efficiency of 80% is obtained at 0 reduced temperature, meaning for an inlet temperature equal to the ambient temperature. With increasing inlet temperature, the thermal losses to the ambient increase, and as a result, the thermal efficiency decreases. For very high inlet temperature, the thermal efficiency drops below 0. At this point, the water flowing in cannot be heated any further. The red line shows the measured thermal efficiency of an evacuated tube collector. At 0 reduced temperature, it has an efficiency of 60%, which is lower than the flat plate collector. However, the efficiency curve has a much lower slope, meaning that it outperforms the flat plate collector at higher inlet temperatures. It's interesting to observe that in both cases, the efficiency is a linear function of the reduced temperature. We can understand that using a heat flow model. Note that this is a simplified model that ignores factors like wind speed and the angle of the incoming sunlight. We will analyze the heat flows per square meter of collector area. In steady state conditions, there is a balance between, on the one hand, the solar radiation absorbed by the absorber plate, and on the other hand, the heat lost to the ambient and given off to the water. Of the incoming solar irradiance, we assume a fraction alpha is absorbed. The remaining is lost, for example, through reflection. We also assume that the loss to ambient is proportional to the temperature difference between absorber and ambient. Here, H ambient is the effective heat transfer coefficient that includes conduction, radiation, and convection. We make a similar assumption for the heat transfer from the absorber to the water. If we then calculate the thermal efficiency and make some simplifying assumptions, we find that the thermal efficiency is indeed a linear function of reduced temperature. At zero reduced temperature, the thermal efficiency is equal to optical absorption factor alpha. The slope of the curve is equal to the heat transfer coefficient from absorber to ambient. This explains the difference between the efficiency curves we saw before. The evacuated tube collector absorbs less of the incoming light. It has a lower alpha, but it has a lower heat loss to the ambient and therefore a less negative slope. The year average thermal efficiency depends not only on the type of collector, but also on the required temperature. For a low temperature application, such as pool heating, this collector may achieve a 60% year average thermal system efficiency, while for a higher temperature application, the same collector might reach only 20% efficiency. If we assume a year average thermal efficiency of 40%, this means that in a temperate climate with an irradiance of 1000 kWh per square meter, the solar thermal system can generate 400 kWh per square meter. This is more than double the energy yield of a photovoltaic system. We must keep in mind, however, that 1 kWh of thermal energy typically has a lower value than 1 kWh of electrical energy. Finally, I'd like to introduce the PVT hybrid collector that integrates photovoltaic module and the solar thermal collector into one device that generates electricity and heat simultaneously. Because of additional losses, the electrical and thermal efficiency of this PVT collector are usually a bit lower than the electrical and thermal efficiencies of the PV module and the solar thermal collector respectively. However, when we compare on the one hand 1 square meter solar thermal collector next to 1 square meter of PV panel side by side, to on the other hand a 2 meter PVT panel, then the energy yield of the PVT collector is larger. This means that the hybrid PVT system can be used when both electricity and heat are needed, but roof space is limiting. This brings me to the end of this lecture. We have discussed PV modules that generate electricity and solar thermal collectors that generate heat. We compared different types of solar thermal collectors, such as the flat plate, evacuated tube, and hybrid PV thermal collector. We also used a simple thermal model to understand how the optical absorption factor and the heat loss to the ambient affect the thermal efficiency curve.